In 1997, a physicist at the University of Washington took two metal plates, coated them in gold, placed them inside a vacuum chamber, and measured a force that should not exist. There was nothing between those plates. No air, no radiation, no particles of any kind. The space between them was as empty as space can physically be. And the plates moved. They pushed toward each other with a force that matched to within 5%, a prediction made 49 years earlier by a Dutch physicist who had been working at an electronics company, studying the viscosity of paint. The prediction said that empty space is not empty, that the vacuum of the universe contains energy, that nothingness, actual literal nothing, pushes back. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon. Link is in the description. That experiment was confirmed the following year to 1% precision using a completely different technique. Then confirmed again. Then confirmed at Harvard using microelectromechanical systems. Then, in 2011, a team at Chalmers University in Sweden did something that sounds impossible even when you describe it in the driest possible terms. They did not just measure the energy in empty space, they shook the vacuum hard enough to create real, detectable photons. Light out of nothing. Published in Nature. Replicated independently 2 years later. So here is the part that should bother you. When you use quantum field theory, our best mathematical description of the subatomic world, to calculate the total energy in a single cubic meter of empty space, you get a number. That number is 10 to the 113th power joules. To put that in perspective, the total energy of the entire observable universe, every galaxy, every star, every planet, every photon of light, every particle of matter, everything is estimated at around 2.2 times 10 to the 69th joules. 1 cubic meter of vacuum, according to our best theory of particle physics, should contain more energy than the entire observable universe by 44 orders of magnitude. And when cosmologists actually measured how much vacuum energy seems to exist, based on the rate at which the expansion of the universe is accelerating, they got a number that is 120 orders of magnitude smaller than the prediction. That is not a rounding error. That is the single worst prediction in the history of physics. It has been called exactly that, in textbooks, in journal articles, in Scientific American, and the response from the physics establishment has not been to solve it. The response, over a period of decades, has been to quietly reclassify the entire question as philosophy and move on. I have been reading about this for weeks, and I need to be honest with you. The thing that keeps me coming back to this topic is not the discrepancy itself, as staggering as it is. It is the reaction to the discrepancy. Because this is not fringe science. This is not some guy on the internet claiming he cracked the secret of free energy. This is quantum electrodynamics, the most precisely confirmed theory in the history of science, accurate to 12 decimal places for the anomalous magnetic moment of the electron, the crown jewel of modern physics. And it contains a quantity, vacuum energy, whose physical reality the entire field has decided it cannot determine. The most successful theory ever built by human beings has something at its mathematical core that the people who use it every day refuse to say is real. I personally think this is the most underrated crisis in all of physics. It gets almost no public attention compared to dark matter, or quantum computing, or the search for gravitational waves. And the reason is not that it is less important, The reason is that it is more uncomfortable, because it sits at the exact point where our two most trusted theories, quantum mechanics and general relativity, collide, and it proves they cannot both be right. Not in some abstract, hypothetical way, in a way that is off by a factor of 10 to the 120th power. And that question, what is the quantum vacuum? What does it contain? And why has physics refused to answer? Is what this entire video is about. But this story does not start in a modern laboratory. It starts with a quiet, grieving man working alone in Berlin, who was trying to undo his own greatest discovery. Berlin, 1911. Max Carl Ernst Ludwig Planck was 53 years old. He had been born in Kiel in 1858 into a family of scholars. His great-grandfather and grandfather had both been theology professors at Göttingen. His father taught constitutional law at Munich. Planck chose physics, despite a warning from his professor Philipp von Joly, who told the young student that in physics, almost everything had already been discovered, and all that remained was to fill a few unimportant holes. Planck later recalled this advice with dry amusement. He chose physics anyway, he said, not because he expected to make great discoveries, but because he found its fundamental truths so deeply fascinating that he could not help himself. 2 years before 1911, Planck's first wife, Marie Merck, had died of tuberculosis. They had been married 22 years. They had 4 children together, and every one of them would meet a fate so cruel that it reads like the work of a malicious dramatist. But in 1911, those tragedies were still ahead. What Planck carried in that year was the more immediate weight of grief and the intellectual burden of a discovery he profoundly distrusted. His quantum hypothesis, published in 1900, had shattered the classical picture of energy. Electromagnetic radiation came in discrete packets, quanta, not in smooth continuous waves. The idea explained the spectrum of black body radiation, a problem that had defeated every attempt at a classical solution. It would earn him the Nobel Prize in 1918. And Planck hated it. He spent the better part of a decade trying to demonstrate that quantization was merely a mathematical trick, a calculational convenience, rather than a statement about physical reality. And in 1911, he published what historians now call his second quantum theory, presented in the Proceedings of the German Physical Society under the title Eine neue Strahlungshypothese, a new radiation hypothesis. This reformulation assumed that oscillators absorbed energy continuously, the way classical physics said they should, but emitted it only in discrete quantum jumps. It was a compromise. 1 foot in the quantum world, 1 still planted firmly in the classical. The mathematics produced something Planck did not expect. When he derived the average energy of an oscillator under this new scheme, the formula contained the usual Planck distribution, the term that described how energy depended on temperature, plus an additional residual term, 1/2 h nu, half a quantum of energy that refused to go to zero. Even at absolute zero temperature, even when all thermal energy had been drained away, this residual energy persisted. The oscillator could not be perfectly still. He published a more formal derivation in the Annalen der Physik the following year. He noted the term, he discussed what it might mean, and then, consumed by his larger project of reconciling quantum theory with classical mechanics, he moved on. He did not pursue it. He had no idea that this half-quantum, this ghost in the equation, would become one of the deepest unresolved problems in the history of human inquiry into the nature of reality. 2 years later, Albert Einstein picked it up. Working with Otto Stern, Einstein published some arguments for the assumption of molecular agitation at absolute zero in the Annalen der Physik in 1913. They calculated the specific heat of hydrogen gas at low temperatures and compared the theory against the experimental measurements of Arnold Eucken. With 0-point energy included, the theory matched the data beautifully. Without it, the predictions diverged qualitatively. Even more remarkably, Einstein and Stern showed that you could derive Planck's entire radiation law using 0-point energy without any assumption of quantum discontinuity. That result implied 0-point energy might be more fundamental than the quantum hypothesis it emerged from, which was a genuinely radical suggestion. And then Einstein changed his mind. At the Second Solvay Congress in late October of 1913, he publicly abandoned the concept. In a letter to Paul Ehrenfest, he called it Morse tot, dead as a doornail. Further analysis had revealed what he believed were fatal contradictions in the way 0-point energy was used to derive the radiation law. Einstein, who had a remarkably honest relationship with his own errors, moved on without looking back. The concept drifted in limbo for 14 years. A handful of theorists discussed it. Nobody treated it as urgent. And then, in 1927, Werner Heisenberg published a paper that buried 0-point energy so deep in the foundations of quantum mechanics that no amount of intellectual discomfort could ever dig it out. The uncertainty principle, delta x times delta p, is greater than or equal to h bar over 2. The position and momentum of a particle cannot simultaneously be known with arbitrary precision. This is not a limitation of our instruments. It is not about the clumsiness of measurement. It is a structural feature of reality. And it had a devastating consequence for the classical picture of absolute stillness. Consider a particle in a harmonic potential, an atom vibrating in a crystal lattice, a mode of the electromagnetic field oscillating in space. If that particle were truly at rest at the bottom of its potential well, its position would be exactly defined, sitting at the minimum, and its momentum would be exactly zero, both simultaneously known with perfect precision. That would violate the uncertainty principle. Therefore, the particle cannot be at rest. It must jitter. It must retain some minimum kinetic and potential energy, no matter how cold the system becomes, no matter how much energy you remove. That minimum is 1/2 h bar omega, the 0-point energy. What Planck stumbled upon through mathematical compromise in 1911, what Einstein briefly championed and then killed in 1913, Heisenberg rendered logically inescapable in 1927. Every quantum harmonic oscillator in the universe possesses an irreducible ground state energy. Every vibrating atom, every electromagnetic mode, you cannot remove it. The energy is a consequence of the deepest structural principle of quantum mechanics. And here is where the implications expanded beyond anything those early physicists could have anticipated. Because quantum field theory, developed through the 30s and 40s by Dirac, Heisenberg, Pauli, Jordan, Tominaga, Schwinger, Feynman, and Dyson, applied this insight not just to atoms and oscillators, but to the vacuum of space itself. In quantum field theory, the universe is described not as particles floating in emptiness, but as a set of continuous fluctuating fields permeating every point in space. The electromagnetic field, the electron field, the muon field, the quark fields, the gluon fields, the Higgs field. Each of these fields must be quantized, meaning each point in space supports modes that behave as quantum harmonic oscillators. And even in the vacuum state, the ground state with no real particles present, each oscillator retains its zero-point energy. This means the electric and magnetic fields do not sit at zero in the vacuum. They fluctuate around a mean of zero. The fluctuations are real. The average of the field is zero. But the average of the field squared is not zero, just as the average position of a vibrating atom might be at the center of its potential well, while its average kinetic energy is clearly not zero. The vacuum seethes with these fluctuations. Virtual particle-antiparticle pairs, electrons and positrons, quarks and antiquarks, appear spontaneously from the vacuum and annihilate within timescales permitted by the energy-time uncertainty relation. They are not metaphorical. They interact with real particles before they vanish. Virtual electron-positron pairs near an electric charge screen that charge through an effect called vacuum polarization, making the fine structure constant energy dependent. This is measured, confirmed, part of the standard model of particle physics. When you sum up the zero-point energies of all modes of all fields across all possible frequencies, using the Planck scale as a natural high-energy cutoff at approximately 10 to the 18th gigaelectron volts, the energy of the vacuum comes out to approximately 10 to the 113th joules per cubic meter. That is not a theoretical estimate with large error bars. That is a straightforward calculation from our best understood theory, using a cutoff that every physicist agrees is the natural boundary of our knowledge. I spent 3 hours, one night, trying to make this number feel real, and I failed. Nothing works. Richard Feynman and John Wheeler reportedly estimated that a single teacup of empty space contains enough zero-point energy to boil all the world's oceans. Pauli calculated in the 1920s that if the energy were real and gravitating, the observable universe could not extend past the moon. Wilhelm Lenz ran the same calculation in 1926. The sun's core energy density is about 10 to the 13th joules per cubic meter. The theoretical vacuum exceeds the center of the sun by 100 orders of magnitude. A single cubic centimeter of empty space, according to quantum field theory, outweighs the observable universe. And yet the universe is 14 billion years old. Galaxies formed, stars ignited. You are watching this. Something is catastrophically wrong with the prediction, or catastrophically wrong with our understanding of what the prediction means. The story of how physics discovered this discrepancy, failed to resolve it, and eventually stopped trying begins with the most unlikely possible starting point. Mayonnaise, Eindhoven, Netherlands, 1942. The country was under German occupation. Leiden University had been shut down by the Nazis in November 1940, after students and faculty protested the dismissal of Jewish professors. The intellectual life of Dutch physics had been strangled, and Hendrik Brucht Gerhard Casimir, 33 years old, one of the most gifted theoretical physicists in Europe, had taken refuge at the Philips Natuurkundig Laboratorium in Eindhoven, the research wing of the Philips Electronics company. His job was to study colloidal solutions, paints, adhesives, mayonnaise, the physical behavior of viscous substances with microscopic particles suspended in them. I realize that sentence sounds like the setup for a joke. It is not. The man who would prove that empty space pushes back spent the war years studying condiments, and the connection between mayonnaise and the quantum vacuum is direct, documented, and one of the strangest origin stories in all of physics. Casimir had been born in The Hague on July 15, 1909. His education reads like a tour of the greatest physics departments of the early 20th century. He studied at Leiden under Paul Ehrenfest, a brilliant and deeply troubled physicist who was a close friend of both Einstein and Bohr. As a graduate student, Casimir spent roughly 18 months in Copenhagen working directly with Niels Bohr, an experience he later described as transformative. He completed his PhD at Leiden in 1931 with a thesis on the quantum mechanics of rigid rotating bodies. Then he spent a year as Wolfgang Pauli's assistant at ETH Zurich, where he absorbed Pauli's legendary combination of brilliance and brutality. During the Leiden years, Casimir also co-developed the Gorter-Casimir 2 fluid model of superconductivity with C.J. Gorter, a phenomenological theory that preceded the full BCS explanation by 2 decades. He contributed the Casimir operator to the mathematics of Lie groups. He was, by every measure, operating at the highest level of theoretical physics. When he left academia for Phillips in 1942, Pauli was genuinely baffled. He addressed letters to Casimir as Herr Director, dripping with sarcasm. The supreme irony of Casimir's career is that his most famous contribution to physics, the one that would outlast everything else he did, emerged directly from the industrial work Pauli found so beneath him. Casimir's colleague, Theo Overbeek, working with E.J.W. Verwey on what would become the DLVO theory of colloidal stability, had noticed that Fritz London's 1930 theory of van der Waals forces could not explain their measurements. The attractive force between colloidal particles was falling off at long range faster than London's equations predicted. Overbeek suspected retardation effects, modifications due to the finite speed of light. He asked Casimir to look into it. Working with Dirk Polder, Casimir calculated the retarded van der Waals force. The results appeared in Physical Review on February 15, 1948. They found that at large separations, the interaction between an atom and a surface falls off as 1 over r to the 4th rather than 1 over r to the 3rd, and between 2 atoms as 1 over r to the 7th rather than 1 over r to the 6th. The full calculation was, as the Soviet physicist Evgeny Lifshitz later noted, laborious and lengthy. Heavy algebra, careful bookkeeping, pages and pages of derivation. But the final answer was disturbingly simple, suspiciously clean. And when Casimir mentioned this surprising simplicity to Niels Bohr during a visit, Bohr mumbled something about zero-point energy. That is a direct quote from Casimir's own account. Bohr mumbled something. One of the most consequential hints in the history of physics was delivered as a mumble by a 70-year-old man who may not have fully realized what he was suggesting. Casimir went back to his desk and reformulated the entire Casimir-Polder problem from the perspective of vacuum fluctuations instead of the electromagnetic interactions between atoms. The laborious multi-page derivation collapsed into roughly 2 pages. The simplicity was not a coincidence, it was a message. The deepest explanation for van der Waals forces at long range was not electromagnetic interactions between atoms. It was the quantum structure of empty space. And then Casimir took what he called the obvious extension. Instead of computing the force between an atom and a wall, he computed the force between 2 walls, 2 uncharged, perfectly conducting parallel metallic plates placed in a vacuum with absolutely nothing between them. The result was published in the Proceedings of the Royal Netherlands Academy of Arts and Sciences, Volume 51, page 793, 1948. And the physics is clean enough to explain without a single equation. Take two perfectly flat, perfectly conducting metal plates, stand them parallel to each other with a tiny gap between them. Put the whole thing in a vacuum. Now think about the electromagnetic field between those plates. The field can only support modes, standing waves, whose wavelengths fit a whole number of times into the gap. If the gap is small, only short wavelengths fit. Many modes are excluded. Outside the plates, no such restriction exists. Every wavelength is allowed. Every mode is present. Each electromagnetic mode carries a 0-point energy of 1/2 h-bar omega. There are more modes outside the plates than between them. Therefore, the 0-point energy density is higher outside than inside. This difference in energy density creates a radiation pressure. The vacuum itself pushes the plates together. The formula Casimir derived is pi² times h-bar times c, divided by 240 times d to the 4th power, where d is the plate separation. Only the fundamental constants h-bar and c appear. The electron charge is nowhere in the formula. At a separation of 1/10 of a micrometer, the pressure is equivalent to roughly 1 atmosphere. That is a real, physical, measurable force being exerted by empty space on matter. In 1948, nobody on Earth could measure it. The prediction sat essentially untested for decades. Marcus Sparnay at Philips tried in 1958 using flat metallic mirrors and a spring balance. His result had uncertainties of up to 100%. His conclusion, which became famous in its own right, was that the results did not contradict Casimir's theoretical prediction. That is physicist speak, for the experiment was inconclusive. Electrostatic contamination, surface roughness, and the impossibility of aligning two plates to nanometer precision at nanometer separations made the measurement a nightmare. The definitive confirmation took nearly half a century. In 1997, Steve Lamoureux, who would go on to become the Eugene Higgins Professor of Physics at Yale, cracked the problem with an elegant geometric insight. Instead of trying to hold two parallel plates at nanometer separation, which requires alignment precision that borders on the impossible, he measured the force between a flat plate and a sphere. A sphere near a flat surface does not need to be aligned. You just bring it close. His torsion pendulum apparatus used a 4-centimeter gold-coated spherical lens and a flat quartz plate, both coated with copper and gold. He measured the twisting force on a horizontal bar suspended by a tungsten wire as the sphere approached the plate. The result, published in Physical Review Letters on January 6, 1997, confirmed Casimir's prediction to within 5%. The New York Times ran a full-page article on January 21st. Physicists confirm power of nothing, measuring force of universal flux. The subtext was unmistakable. Empty space pushes, and we can measure how hard. 1 year later, Umar Mohideen and Anushri Roy at UC Riverside obliterated the error bars using an atomic force microscope. Their gold-coated polystyrene sphere was tiny, 196 micrometers in diameter, and they measured forces at plate separations as small as 1/10 of a micrometer. The result, published in Physical Review Letters in November 1998, showed agreement with theory to approximately 1%. The root mean square deviation was 1.6 piconewtons. A piconewton is a trillionth of a newton. They were measuring the push of nothing to a trillionth of a newton precision. In 2001, a team at the University of Padua achieved the first measurement in the original parallel plate geometry using microresonators. The same year, the Capasso group at Harvard demonstrated the Casimir force actuating a microelectromechanical device published in Science, showing the effect was not just measurable, but technologically relevant. And in 2009, Munday, Capasso, and Parseghian published a result in Nature, demonstrating repulsive Casimir forces, what the press called quantum levitation, between a gold surface and silica immersed in the liquid bromobenzene. They had figured out how to make the vacuum push things apart instead of together. Hendrik Casimir died on May 4, 2000, in Hees, Netherlands. He was 90 years old. He had lived long enough to see Lamoureux's 1997 confirmation, just barely. The prediction he made at a corporate lab during the Nazi occupation, inspired by a mumble from Niels Bohr, derived in roughly 2 pages, had been confirmed to extraordinary precision. The vacuum pushes. That is settled. But what the vacuum is, and how much energy it contains, and why that energy does not tear the universe apart, those questions were very much not settled. And they are not settled now, because the confirmation of the Casimir effect did not close the case. It blew it wide open. If the vacuum contains energy, if that energy exerts a measurable physical force, then the cosmological constant problem is not just a theoretical curiosity, it is a crisis. The energy that pushes those plates together should, according to the same theory that predicts it, be 10 to the 120th times larger than what the universe actually seems to contain. The scientific community celebrated Lamoureux's result and Mohiuddin's refinement as elegant confirmations of quantum electrodynamics, which they were. But there was a darker implication underneath the celebration that most of the press coverage did not touch, and that most physicists at the time preferred not to discuss publicly. If the Casimir effect is real, if the vacuum really does exert a measurable force derived from its zero-point energy content, then that energy is physical. It exists. And if it exists, it gravitates. And if it gravitates, then the prediction of 10 to the 113th joules per cubic meter is not an abstract mathematical embarrassment. It is a physical catastrophe, because energy that gravitates at that density should have destroyed the universe before it formed. The confirmation of the Casimir effect did not close the case on vacuum energy. It made the case worse. Every improvement in precision, every new experimental technique that agreed with the prediction, every decimal place of confirmation, tightened the noose on the cosmological constant problem. The better the evidence for vacuum energy became, the more impossible the discrepancy grew. And the Casimir effect was not the only evidence. It was not even the strongest evidence. There was another experiment, conducted a year before Casimir published his prediction, that showed the vacuum doing something even more intimate and even more disturbing. Not pushing metal plates together from the outside, reaching inside a single hydrogen atom and rearranging its energy levels from within. June 2nd, 1947. Shelter Island, New York. The Ram's Head Inn, a modest establishment at the eastern tip of Long Island, hosted 24 of America's leading physicists for a 3-day conference on the foundations of quantum mechanics. The organizer, Duncan McInnes of the Rockefeller Institute, had a budget of $850. The attendees included J. Robert Oppenheimer, who chaired the meeting, Richard Feynman, Julian Schwinger, Hans Bethe, John Archibald Wheeler, John von Neumann, Hendrik Kramers, David Bohm, Victor Weisskopf, and a careful, methodical experimentalist from Columbia University named Willis Lamb, accompanied by his graduate student Robert Rutherford. Schwinger later recalled the atmosphere. It was the first time that people who had all this physics pent up in them for 5 years could talk to each other without somebody peering over their shoulders and saying, "Is this cleared?" The war was over. Los Alamos was winding down. The scientists who had built the bomb were free, for the first time since 1941, to think about physics for its own sake. Lamb presented the result that detonated the conference. Working at the Columbia Radiation Laboratory with surplus microwave equipment developed for wartime radar, Lamb and Rutherford had measured something that should not exist. The hydrogen atom has two energy levels designated 2s 1/2 and 2p 1/2. Both sit in the n equals 2 energy shell. Both have the same total angular momentum. According to Dirac's beautiful 1928 relativistic wave equation, the equation that predicted the existence of antimatter, these two levels should have exactly the same energy. They are degenerate in the language of quantum mechanics. Identical. They are not. Lamb showed that the 2s 1/2 level sits higher in energy than the 2p 1/2 level by approximately 1000 megahertz. The modern precision value, refined over decades of increasingly accurate measurements, is 1057.864 megahertz. That is not a small discrepancy. That is a disagreement at the fourth significant figure in the most elegant equation in all of physics. The experimental technique was a masterwork of repurposed wartime technology. Lamb produced a beam of hydrogen atoms, bombarded them with electrons to excite some to the metastable 2s 1/2 state, which has an extraordinarily long lifetime of about 1/8 of a second, because direct decay to the ground state is forbidden by selection rules. He then exposed the beam to tunable microwave radiation. A variable magnetic field shifted the energy levels via the Zeeman effect. When the microwave frequency matched the transition energy between the 2s and 2p states, atoms would transition to the short-lived 2p state and decay rapidly before reaching the tungsten detector. The signal at the detector dropped. By scanning the microwave frequency, Lamb could map the transition and measure the energy difference with remarkable precision. Their paper, Fine Structure of the Hydrogen Atom by a Microwave Method, was received by Physical Review on June 18, 1947, and published August 1st. It was 4 pages long and changed the direction of theoretical physics. Hans Bethe figured out why the shift existed, and he did it on a train. After hearing Lamb's presentation at Shelter Island, Bethe took the 75-mile train from New York to Schenectady, where he was consulting at General Electric's research labs. During that ride, he performed the first successful calculation of the Lamb shift. The key insight came from Hendrik Kramers, who had suggested at the conference that the infinities plaguing quantum electrodynamics could be managed through mass renormalization. The idea was that the electron's self-energy, the energy of its interaction with its own electromagnetic field, is formally infinite in QED. But this infinite self-energy is already folded into the observed physical mass of the electron. You never see the bare mass. You always see the crest mass, the bare mass, plus the self-energy contribution. So you only need to calculate the difference in self-energy between a free electron and an electron bound in a hydrogen atom. That difference is finite. Bette's non-relativistic calculation with a relativistic cutoff produced approximately 1040 MHz, within 4% of Lamb's measured value. The result appeared as a 2-page paper in Physical Review with the title "The Electromagnetic Shift of Energy Levels." It contained only 12 equations. Freeman Dyson later wrote that Bette's calculation broke through a thicket of skepticism and opened the way to the modern era of particle physics. And what is the physical mechanism behind the Lamb shift? Vacuum fluctuations. The electron in a hydrogen atom does not sit in pristine empty space. It is immersed in the seething quantum vacuum, surrounded by zero-point fluctuations of the electromagnetic field. The electron continually emits and reabsorbs virtual photons. These fleeting interactions cause the electron to undergo rapid, random jittering motions, a kind of quantum trembling. This effectively smears the electron's charge over a small volume around its mean position. For S states, where the electron has a non-zero probability of being found right at the nucleus, this smearing has a significant effect. It reduces the time the electron spends at the very bottom of the attractive Coulomb potential well, where the nuclear charge is strongest. That raises the energy. For P states, where the electron has zero probability of being at the nucleus, the smearing changes very little. A competing effect, vacuum polarization, in which virtual electron-positron pairs near the nucleus screen the nuclear charge, contributes a smaller correction of approximately -27 MHz, partially offsetting the self-energy shift. The net result is the observed upward displacement of S states relative to P states. I want to say something about Willis Lamb, the person, because his biography carries an irony that fits this story perfectly. Born July 12, 1913, in Los Angeles. Bachelor's in chemistry from UC Berkeley in 1934. PhD in physics from Berkeley in 1938, under J. Robert Oppenheimer, with a dissertation on electromagnetic properties of nuclear systems. He declined Oppenheimer's invitation to join the Manhattan Project. Think about that. The man who would use wartime radar technology to probe the vacuum said no to building the bomb, even when his own thesis advisor asked. His career after the Lamb shift spanned Columbia, Stanford, Oxford, as Wykeham Professor of Physics, Yale, and finally the University of Arizona. He won the Nobel Prize in 1955, shared with Polycarp Kusch, for precision measurements of the magnetic moment of the electron. Despite his landmark contribution, or perhaps because of what it taught him about the gap between formalism and understanding, Lamb spent his later career as a vocal skeptic of interpretive overreach in quantum mechanics. He was famously hostile to the word photon, writing an article titled Anti-Photon, in which he argued the concept was overused and poorly understood. He required students entering his lab to pay a 5-cent fine if they used the word. He died in Tucson, Arizona on May 15, 2008, at 94. And there is a third independent line of evidence for vacuum energy that ties the knot even tighter. Spontaneous emission. An excited atom sitting in apparently empty space with no external perturbation of any kind spontaneously drops to a lower energy state and emits a photon. In classical physics, nothing triggers this transition. There is no field to perturb the atom. In quantum electrodynamics, the trigger is the vacuum itself. The zero-point fluctuations of the electromagnetic field couple the excited state to the ground state and induce the emission. Theodore Welton wrote in 1948 that spontaneous emission can be understood as forced emission taking place under the action of the fluctuating field. The vacuum is the stimulus. The decisive proof is environmental. If you place a light emitter inside a microcavity that suppresses certain electromagnetic modes, certain wavelengths that the cavity geometry forbids, the spontaneous emission rate at those frequencies drops. If you place the emitter in a cavity that enhances certain modes, the rate increases. This is the Purcell effect, and it is the foundation of cavity quantum electrodynamics. If spontaneous emission were intrinsic to the atom, if it were a property of the atom alone, then modifying the surrounding vacuum should not change the emission rate. It does. The vacuum plays an active role. So by the late 20th century, the evidentiary picture was overwhelming. The Casimir effect, confirmed to 1%. The Lamb shift, confirmed to 8 decimal places by measurements of extraordinary refinement. Spontaneous emission, manipulated and controlled by modifying vacuum boundary conditions. 3 completely independent physical systems. 3 different experimental techniques. 3 separate groups of physicists, all converging on the same conclusion. The vacuum contains energy. That energy has real, measurable, physical consequences. It pushes metal plates. It shifts atomic spectra. It triggers photon emission. And yet, the most basic question about this energy, the question of whether it is physically real or merely a mathematical artifact that produces correct predictions without corresponding to anything in nature, has never been definitively answered. That sentence sounds absurd. I know, but let me show you why it is true and why the gap between the evidence and the interpretation matters more than almost any other open question in physics. The cosmological constant problem, also called the vacuum catastrophe, was given its dramatic name in 1995 by Ronald Adler, Brendan Casey, and Ovid Jacob in a paper in the American Journal of Physics. But the problem itself is much older than its name. Pauli recognized it in the 1920s. Wilhelm Lenz wrote about it in 1926. For most of the 20th century, physicists handled it with a trick called normal ordering, which amounts to rearranging the mathematical operators so the zero-point energy terms cancel. You declare that only energy differences are physically meaningful. Subtract the infinite vacuum energy by hand, set the result to 0, and carry on. In quantum mechanics, this works perfectly. Energy differences are all that matter. You can put the 0 of your energy scale wherever you want. It is like choosing sea level as the reference for measuring altitude. The altitude of Denver does not change if you switch your reference to the center of the Earth. But general relativity does not grant this freedom. In Einstein's theory of gravitation, absolute energy matters. All energy curves, space-time, all energy gravitates. If the vacuum of space contains energy, that energy enters the gravitational field equations as a cosmological constant. And if the vacuum energy density is anywhere close to what quantum field theory predicts, the universe would have ripped itself apart or collapsed in on itself within a vanishingly small fraction of a second. After the Big Bang, there would be no atoms, no stars, no galaxies, no one to notice the problem. The universe obviously exists. Therefore, the vacuum energy density is not 10 to the 113th joules per cubic meter. The actually observed value became available in 1998 when two independent teams announced one of the most startling discoveries in the history of astronomy. The Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with key analysis by Adam Rees at Johns Hopkins, had both been measuring the brightness of distant Type Ia supernovae. These stellar explosions have a remarkably consistent intrinsic luminosity, making them useful as standard candles for measuring cosmic distances. By comparing observed brightness with known intrinsic luminosity, you can determine how far away a supernova is. And by measuring the redshift of its host galaxy, you can determine how fast it is moving away. Both teams expected to find that the expansion of the universe was slowing down. Gravity, after all, should be pulling everything back together. What they found was the opposite. The distant supernovae were dimmer than expected, meaning farther away than expected, meaning the expansion rate had been increasing, not decreasing. The universe is accelerating. Something is pushing it apart. Science magazine named it the breakthrough of the year in December 1998. The Nobel Prize in Physics went to Perlmutter, Schmidt, and Reis in 2011. And the something that is pushing the universe apart behaves exactly like a cosmological constant, exactly like vacuum energy. The observed value, based on Planck satellite data from 2015, is approximately 5.36 times 10 to the negative 10th joules per cubic meter. Compare that with the quantum field theory prediction of 10 to the 113. The ratio is 10 to the 120th, 1 followed by 120 zeros. That is the vacuum catastrophe. Let me try to make you feel this number, because I think most of the time when people hear 120 orders of magnitude, it washes over them. It sounds like a lot. The word fails completely. It is a quantity so far beyond human intuition that no analogy truly captures it. But I am going to try anyway. The mass of the entire observable universe is roughly 10 to the 53rd kilograms. The mass of a single proton is about 10 to the negative 27 kilograms. The ratio is 10 to the 80th. That is the biggest ratio most physicists ever encounter in their careers, the ratio between the largest thing and one of the smallest things. The vacuum catastrophe is 40 orders of magnitude larger than that. If you took the ratio between the universe and a proton and then multiplied it by the ratio between the universe and a proton again, you still would not be there. You would need to multiply by another factor of 10 to the 40th, which is itself roughly the ratio between the diameter of the observable universe and the diameter of a hydrogen atom. The phrase, "the worst theoretical prediction in the history of physics," appears in the Cambridge University Press textbook, General Relativity, by Hobson, Evstathio, and Lassenby. Antonio Padilla of the University of Nottingham called it one of the most awkward, embarrassing, difficult problems in theoretical physics. Scientific American has called it physics's most embarrassing problem. That is not hyperbole. There is no other prediction in any branch of science that is wrong by 120 orders of magnitude. So what has the field tried? Supersymmetry was the first serious hope. In a supersymmetric theory, every boson has a fermionic partner, and vice versa. The vacuum energy contributions from bosons are positive. The contributions from fermions are negative. If the symmetry is exact, They cancel perfectly and the vacuum energy is zero. Beautiful, elegant, and wrong because supersymmetry is broken in our universe. If it exists at all, the superpartner particles are much heavier than the particles we observe, which means the cancellation is imperfect. Even the most generous supersymmetric models reduce the discrepancy from 120 orders of magnitude to about 55 or 60. That is like owing $1 trillion and proudly announcing you negotiated it down to $1 billion. Technically less, practically catastrophic. String theory offers the landscape, a staggeringly vast collection of roughly 10 to the 500th possible vacuum configurations, each with different values of physical constants, including the cosmological constant. The argument is anthropic. We find ourselves in one of the rare vacua where the cosmological constant happens to be small enough for structure to form, because in the other vacua, there are no observers to ask the question. Steven Weinberg anticipated this reasoning in a remarkable 1987 paper in Physical Review Letters, titled Anthropic Bound on the Cosmological Constant, predicting that the cosmological constant should be close to the largest value compatible with galaxy formation. His prediction turned out to be surprisingly close to the value eventually measured, which is either a profound vindication of anthropic reasoning or an extraordinary coincidence, depending on your philosophical commitments. But a large fraction of the theoretical physics community views anthropic reasoning with something between discomfort and outright hostility. It explains why we observe a particular value without explaining why the value is what it is. And to many physicists, an explanation that works equally well for any value of a parameter as long as observers exist to see it is not an explanation at all. It is a concession of defeat dressed up in mathematical language. There have been other attempts. Quintessence models propose a slowly evolving scalar field that could mimic a cosmological constant at late cosmic times, but has a fundamentally different origin. Vacuum decay models suggest the universe might tunnel quantum mechanically from a metastable false vacuum to a true vacuum with lower energy, a process that would be catastrophic, but might resolve the energy discrepancy in the process. Some theorists have proposed that vacuum energy somehow does not gravitate, that there is a mechanism that decouples it from the gravitational field equations, but nobody has been able to construct such a mechanism without breaking something else in the theory. And some have simply proposed that the bare cosmological constant in Einstein's equations has a value that almost perfectly cancels the quantum vacuum energy, leaving only the tiny observed residual. But that cancellation would need to be accurate to 120 decimal places. There is no known physical principle that would produce such a cancellation. It would be like balancing your checkbook and finding that your income and expenses, both in the trillions of dollars, agree to the penny by sheer coincidence. Possible in principle, absurd in practice. And then, in March of 2005, the game may have changed. The DESI collaboration, the Dark Energy Spectroscopic Instrument, released its Year 3 results. DESI is a robotic instrument mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, capable of measuring the spectra of 5,000 celestial objects simultaneously. Its Year 3 analysis used data from over 14 million galaxies and quasars to map the expansion history of the universe across 11 billion years. The headline result was 4.2 sigma evidence that the dark energy equation of state parameter W is not constant. If W equals exactly -1, dark energy is a cosmological constant, static, unchanging, a fixed property of empty space. DESI's data suggests W is evolving over time. Dark energy may be getting stronger, or weaker, or oscillating. The static vacuum of textbook quantum field theory may be wrong not just in its magnitude, but in its very nature. 4.2 sigma is tantalizingly close to the 5 sigma threshold that physics conventionally requires to claim a discovery. Nature Astronomy published an editorial titled "The Inconstant Cosmological Constant." If DESI is right, the vacuum catastrophe is not just a calculation gone wrong. It is a sign that we fundamentally misunderstand what the vacuum is. A static vacuum energy wrong by 120 orders of magnitude is one kind of problem. A vacuum that changes with time, whose energy density evolves as the universe ages, is a completely different kind of problem, and it is a problem that no existing theory is equipped to handle. Everything was in place for a genuine reckoning. Every line of evidence pointed to the same conclusion. The vacuum is not what we were taught. And instead of confronting that, the establishment did something I find genuinely difficult to forgive. It moved the question to a different department. In 2005, Robert Jaffe, the Jane and Otto Morningstar Professor of Physics at MIT, former director of MIT's Center for Theoretical Physics, published a paper in Physical Review D that quietly changed the terms of engagement for the entire field. The paper was titled "Casimir Effect and the Quantum Vacuum." Its abstract contained a sentence that landed like a depth charge. In discussions of the cosmological constant, the Casimir effect is often invoked as decisive evidence that the zero-point energies of quantum fields are real. On the contrary, Casimir effects can be formulated and Casimir forces can be computed without reference to zero-point energies. One of the most respected theorists in the world had just told the physics community that their go-to proof of vacuum energy, the experiment everyone pointed to, the one confirmed to 1%, does not actually prove what everyone says it proves. Jaffe's argument was technical, but devastating. The standard derivation of the Casimir effect treats the force as a difference in vacuum energy density between the inside and outside of the plates. That derivation produces a formula that appears to depend only on the fundamental constants h bar and c, with no dependence on the fine structure constant alpha, which characterizes the strength of electromagnetic interactions. This alpha independence makes it look like a pure vacuum phenomenon, something arising directly from the geometry of empty space, independent of the electromagnetic coupling between light and matter. Jaffe showed this is misleading. When you model the plates realistically as materials with finite conductivity rather than as perfect conductors, the Casimir force depends on the material properties of the plates, which in turn depend on alpha. The clean alpha-independent formula is not a deep result. It is the limit where alpha goes to infinity, the regime of infinitely strong coupling. And the Feynman diagrams that contribute to the Casimir force are not vacuum-to-vacuum diagrams, the ones that define zero-point energy. They are diagrams with external lines, standard scattering amplitudes, the same kind of diagrams you compute for any electromagnetic interaction. Jaffe's concluding statement was carefully worded and profoundly important. He wrote that the Casimir effect gives no more or less support for the reality of the vacuum energy than any other one-loop effect in quantum electrodynamics. And then he wrote that the question of whether vacuum energy is real was beyond the scope of the paper. Read that again. A full professor at MIT, publishing in the top journal in the field, explicitly declared that whether vacuum energy is physically real is not a physics question. He was not operating alone in this view. Julian Schwinger, co-winner of the 1965 Nobel Prize in Physics, one of the three men who independently formulated quantum electrodynamics, had derived the Casimir effect decades earlier without any reference to vacuum fluctuations. In his source theory framework, published in Letters in Mathematical Physics in 1975, Schwinger defined the vacuum as the state of zero energy, zero momentum, zero angular momentum, zero charge, zero whatever, no fluctuations, no virtual particles. And the Casimir force comes out exactly right. Haravoy Nikolic published a proof in Physics Letters B in 2016, arguing that the Casimir force is fundamentally a van der Waals force between the atoms of the plates, not a vacuum energy phenomenon at all. And Stephen Fulling, co-discoverer of the Fulling-Davies Unruh effect, one of the most important predictions in all of vacuum physics, wrote in a 2022 paper on the arXiv that there is no proof whatsoever that zero-point oscillations exist. A co-discoverer of one of the key effects in the field was saying the underlying phenomenon might not be real. And Hendrik Casimir himself, the man whose name is synonymous with the proof of vacuum energy, he never committed. When physicist Ivar Breivik asked him in 1972 whether the Casimir effect is due to vacuum fluctuations or van der Waals forces, Casimir answered, "I have not made up my mind." He was asked again 11 years later, in 1983. His answer was identical. He died in 2000 without ever deciding, "I think this is the most underappreciated aspect of the entire story." The popular version, the version on Wikipedia, the version in every pop science article and YouTube video I have ever seen on the subject, says the Casimir effect proves the vacuum contains energy. The full picture is considerably more disturbing. The people who know the most about the Casimir effect, including the man it is named after, including a Nobel laureate who formulated QED, including a professor at MIT publishing in the field's top journal, have either denied, doubted, or explicitly refused to endorse the claim that the Casimir effect proves vacuum energy is real. And the mechanism by which the question was moved from physics to philosophy was not formal. No journal changed its submission guidelines. No conference took a vote. The shift was sociological. It happened through culture, through incentive structures, through the slow accretion of professional risk. David Kaiser of MIT described the broader pattern in a 2014 Nature article. After World War II, a culture took hold in physics departments that Kaiser termed "shut up and calculate." Interpretive questions, questions about what the mathematics means rather than what it predicts, were dismissed as philosophical indulgence. Since quantum electrodynamics gives identical predictions whether you treat vacuum energy as real or as a mathematical artifact, since you can derive all the same results using normal ordering, which removes the zero-point terms, or using Schwinger's source theory, which avoids them entirely, or using the standard formalism which includes them, the question of vacuum energy's reality becomes empirically underdetermined. Multiple interpretations are consistent with the data, and in a shut up and calculate culture, empirically underdetermined questions are not physics questions. They are philosophy. They are, institutionally speaking, someone else's problem. John Clauser, who won the 22 Nobel Prize for his experiments testing Bell's inequality, described the enforcement mechanism in blunt terms. A very powerful stigma began to develop within the physics community toward anyone who sacrilegiously was critical of quantum theory's fundamentals. Any physicist who openly criticized or even seriously questioned these foundations was immediately branded as a quack. If questioning the foundations of quantum mechanics gets you branded a quack, imagine what happens when you question the most embarrassing prediction in physics. The vacuum catastrophe is not just an unsolved problem. It is an embarrassment, and embarrassments in institutional cultures do not get funded, promoted, or published. They get avoided. The avoidance was supercharged by the free energy crackpot community. There is a real, thriving, well-funded subculture of people who believe you can build machines to extract usable energy from the quantum vacuum, violating the second law of thermodynamics and achieving perpetual motion. These people run websites, they sell blueprints, they occasionally defraud investors, and they have generated decades of noise that has made any mention of vacuum energy research in serious physics circles feel contaminated by association. John Baez of UC Riverside put it directly. There is a considerable fringe element of people who speculate and fantasize about the possibility of exploiting zero-point energy to achieve various technical marvels and the long-sought perpetual motion. The free lunch crowd has greatly exaggerated the importance of ZPE. The tragedy is that the conflation between legitimate physics and perpetual motion crackpottery worked. It poisoned the well so effectively that real physicists doing real peer-reviewed, mathematically rigorous work were destroyed by proximity to the topic. Harold Puthoff is the most famous case and the most complicated. PhD in electrical engineering from Stanford in 1967, co-author of the standard textbook Fundamentals of Quantum Electronics, published by Wiley, positions at General Electric, Sperry, the National Security Agency. His early papers on zero-point energy appeared in Physical Review D and Physical Review A, top-tier journals. His 1994 paper with Bernhard Heisch and Alfonso Rueda, Inertia as a Zero-Point Field, Lorentz Force, published in Physical Review A, proposed that inertia itself arises from the electromagnetic interaction of matter with vacuum fluctuations. The paper was covered by Science magazine. But Puthoff had also directed the Stanford Research Institute remote viewing program from 1972 through the mid-1980s, testing claims of psychic perception with CIA funding. The program cycled through 6 code names over 2 decades, consumed approximately $20 million, studied subjects including Uri Geller, and was terminated in 1995 after an external review concluded it had never been useful in any intelligence operation. The credibility damage was irreversible. It did not matter that Puthoff's vacuum energy work was mathematically sound and published in peer-reviewed journals. The Parapsychology Association was a permanent stain. His later papers appeared increasingly in fringe venues rather than Physical Review. And yet, while university physics departments would not touch him, the Pentagon kept calling. Through the Advanced Aerospace Weapons System Applications Program, AAWSAP, established in 2007 by the Defense Intelligence Agency at the urging of Senator Harry Reid, approximately $22 million was allocated for research into advanced physics topics. Puthoff authored Defense Intelligence Reference Document Number 5, Advanced Space Propulsion Based on Vacuum, Space-Time Metric Engineering. Eric Davis, also of Puthoff's Institute for Advanced Studies in Austin, authored Document Number 14, Concepts for Extracting Energy from the Quantum Vacuum. The related Advanced Aerospace Threat Identification Program, AATIP, run by Career Intelligence Officer Luis Elizondo, operated from 2007 to 2012. Its existence was revealed by the New York Times on December 16, 2017, in a front-page article about the Pentagon's mysterious UFO program. So, here is the institutional picture. The same vacuum energy research that was too disreputable for university funding was credible enough for the Defense Intelligence Agency. The same questions that would get a physicist marginalized at a conference dinner were being addressed in classified Pentagon reports. If that is not institutional hypocrisy, I honestly do not know what is. Bernhard Heisch tells an even more revealing story. Heisch had no parapsychology baggage. He was, by any measure, a mainstream astrophysicist, 10 years as scientific editor of the Astrophysical Journal, deputy director of the Center for Extreme Ultraviolet Astrophysics at UC Berkeley, senior researcher at Lockheed Martin. His 94 paper with Puthoff and Ruder was Serious Physics, published in Physical Review A, covered by Science. Arthur C. Clarke named the sharp drive in his novel 3001 The Final Odyssey after Sakharov, Heisch, Rueder, and Puthoff. When Heisch founded the California Institute for Physics and Astrophysics in Palo Alto in 1999 to pursue vacuum energy research, relying entirely on private philanthropy because no institutional funding was available for the topic, the institute folded within roughly 3 years. A credentialed astrophysicist with a distinguished publication record could not sustain a research program on this topic in the United States, not because the science was wrong, because the topic itself was professionally radioactive. NASA tried once. Mark Millis led the Breakthrough Propulsion Physics program from 1996 to 2002 at Lewis Research Center, now Glenn Research Center. The program investigated vacuum fluctuation energy, warp drives, and gravity electromagnetism coupling. Total funding over 6 years was $1.2 million. That is less than a single postdoctoral researcher costs at a major university. Over the same period, it produced 14 peer-reviewed journal articles and was cancelled in 2002. Not for scientific failure, but as collateral damage when the Advanced Space Transportation Program was reorganized and eliminated all speculative research below Technology Readiness Level 3. Millis retired from NASA in February 2010 and founded the Tau Zero Foundation as a private nonprofit to continue the work without institutional support. Harold Sonny White, who held a PhD in physics from Rice University and had received the NASA Exceptional Achievement Medal, established the Advanced Propulsion Physics Laboratory, nicknamed EagleWorks, at Johnson Space Center around 2011. White's team investigated Alcubierre warp drive geometries and the EM drive, which claimed to produce thrust without propellant. A DARPA-funded investigation of Casimir cavity structures led to a 2021 publication in the European Physical Journal C that reported the accidental prediction of a nanoscale warp bubble structure. But the EM drive work was refuted by Martin Tajmar of Dresden University of Technology, who concluded in 2018 and 2001 that all measured thrust was attributable to thermal effects. White left NASA in 2018. And then there is Masahiro Hotta. This is the story that I find most infuriating because it has no parapsychology, no EM drive, no crackpottery of any kind, just clean, rigorous physics that was ignored for 15 years because of the topic. Hotta, a professor at Tohoku University in Japan, proposed quantum energy teleportation, in 2008. The protocol is straightforward. You make a measurement of the quantum vacuum at one location, which injects energy into the system. You then communicate information about the measurement results to a distant partner via classical channels. The distant partner uses that information to perform a local operation that extracts energy from their local vacuum state. The total energy is conserved. No free lunch. No second law violation. The protocol exploits the entanglement structure already present in the quantum vacuum as a physical resource. It is legitimate quantum information theory, mathematically airtight, published in reputable journals. And nobody cared. Quantum magazine reported that at first, many researchers ignored this work, suspicious that pulling energy from the vacuum was implausible. At best, his procedure rankled physicists, tired of fielding crackpot proposals. The mere mention of vacuum energy extraction triggered the immune response that decades of free energy charlatans had conditioned into the physics community. Hotter waited 15 years for experimental confirmation. It came in 2023 from two independent groups, a team at the University of Waterloo, led by Rodriguez Briones, Katia Laflamme, and Martin Martinez, used nuclear magnetic resonance and published in Physical Review Letters on March 13th. Kazuki Ikeda at Stony Brook University demonstrated it on IBM superconducting quantum computers. An enhanced protocol was confirmed by a Purdue University team in September 2024. 15 years. A correct, rigorous, experimentally confirmable piece of physics sat ignored for 15 years because it was about vacuum energy, and the culture had decided that was not real physics. That is not how science is supposed to work. That is how fear works. And this is where I want to directly address something I think almost everyone watching this probably believes. You probably think zero-point energy is fringe science, something associated with perpetual motion machines and conspiracy websites and guys selling plans for impossible devices. It is not. It is standard quantum electrodynamics, taught in every graduate physics program in the world. In every QED textbook, the Casimir effect is in the textbooks. The Lamb shift is in the textbooks. Vacuum fluctuation-driven spontaneous emission is in the textbooks. What is fringe is not the energy. What is fringe is asking what it means. The physics is settled. The ontology is forbidden. And the fact that an ontological question about the central quantity in our most precisely confirmed theory can be classified as fringe tells you everything you need to know about the boundaries the establishment has drawn around acceptable inquiry. The formal reclassification, to the extent there is one, can be traced through a series of influential works that gradually moved the question from physics journals to philosophy seminars. Simon Saunders and Harvey Brown's 1991 book, The Philosophy of Vacuum, published by Clarendon Press at Oxford, was explicitly framed as a project in metaphysics. The question of whether quantum vacuum energy is ontologically real, whether it corresponds to something in the world or is merely a feature of the mathematical formalism, was taken up by philosophy of physics specialists at Oxford, USC, and Pittsburgh, the traditional centers of analytic philosophy of science. The interpretation debate mirrors the broader quantum mechanics interpretation debate, with each major school taking a different position on vacuum energy. The Copenhagen and instrumentalist camp says, asking whether zero-point energy is real is meaningless. The quantum state is a calculational tool. Vacuum energy is part of the tool. It gives correct predictions. Asking whether it is real is like asking whether the number 7 is red. It is a category mistake. The Everettian many worlds camp takes the opposite view. If the quantum state is ontologically real, if the wave function describes reality rather than our knowledge of reality, then vacuum fluctuations are real physical processes happening across all branches of the universal wave function. The vacuum is genuinely full of energy. The pilot wave camp, followers of de Broglie and Bohm, would need to reinterpret vacuum fluctuations as features of the guiding field, not as genuine particle creation and annihilation events. And Cubism, the most radically subjectivist interpretation, treats vacuum energy as a feature of an agent's probability assignments, with no objective physical referent at all. Each of these positions is internally consistent. Each generates the same predictions, and physics, as currently practiced, has no experimental way to distinguish among them. The question of vacuum energy's reality has been absorbed into the interpretation problem of quantum mechanics, which has itself been classified by the shut up and calculate culture as not a physics problem. But here is what I cannot get past, and what I think the establishment is wrong about. The cosmological constant problem is not an interpretation problem. It is a quantitative, measurable, experimentally bounded discrepancy. The accelerating expansion of the universe is not a philosophical conjecture. It is data, supernova measurements, baryon acoustic oscillation surveys, cosmic microwave background anisotropy. These are physical observations, and they demand a physical answer to the question of whether vacuum energy gravitates, an answer that cannot be provided without first determining whether vacuum energy is real. The philosophy dodge, in other words, does not work. The universe does not care about departmental boundaries. It has a cosmological constant, or something that behaves like one. That something drives the expansion, and the only candidate explanation we have involves vacuum energy. Dismissing the reality question as philosophical does not make the cosmological constant go away. It just means we are ignoring the only clue we have. But the evidence did not stop at the Casimir effect and the Lamb shift. The vacuum was about to get stranger, and the strangeness went so deep that it challenged the very concept of what emptiness means. Because in 1970, a graduate student at Brandeis University predicted something that sounded like it belonged in a science fiction novel. And 41 years later, a team in Sweden proved he was right. Gerald T. Moore, working on his PhD under H.N. Pendleton III, predicted that a mirror moving at relativistic speeds through the vacuum could convert virtual photons into real photons. The mechanism is conceptually simple, but physically extraordinary. Virtual photon pairs are constantly appearing and disappearing in the vacuum, existing for timescales permitted by the uncertainty principle. Under normal conditions, they vanish before they become real. But if a boundary, a mirror, moves fast enough, it can catch a virtual pair before it annihilates, transferring energy from the mirror's motion into the creation of real particles. Light from nothing, powered by the movement of a surface through empty space. The problem was practical and seemed insurmountable. No physical mirror can move at a significant fraction of the speed of light. A solid object moving at 20 or 30% of light speed would require energies far beyond any existing technology, and it would probably disintegrate long before reaching those speeds. For 4 decades, the prediction seemed experimentally untestable, a beautiful piece of theory with no conceivable path to confirmation. And then Christopher Wilson's team at Chalmers University of Technology in Göteborg, Sweden, found a way around the impossible. Instead of moving a physical mirror, Wilson's group used a squid, a superconducting quantum interference device, at the end of a coplanar waveguide, a sort of highway for microwave photons. The squid acts as a tunable electromagnetic boundary. By rapidly modulating the magnetic field through the squid, oscillating it several billion times per second at frequencies of 10 to 11 gigahertz, the team made the effective boundary of the waveguide vibrate at up to 25% of the speed of light. Not a real mirror moving, the electromagnetic equivalent, a boundary condition flickering in and out so fast that the vacuum could not keep up. The result was published in Nature on November 17th, 2011. Volume 479, pages 376 through 379. The team, which included Goran Johansson, Arsalan Porkabirian, Martin Simone, and Per Delsing at Chalmers, along with collaborators at Riken in Japan and the University of New South Wales, reported that real microwave photons emerged from the vacuum, appearing in pairs. The team confirmed the quantum origin of the photons by detecting two-mode squeezing, a specific quantum correlation between the paired photons that distinguishes genuine dynamic Casimir radiation from any classical noise source. As Goran Johansson explained the physics to reporters, photons appear because they lack mass. Relatively little energy is therefore required in order to excite them out of their virtual state. In principle, he noted, one could also create other particles from vacuum, such as electrons or protons, but that would require a lot more energy. An independent confirmation came in March 2013 when P. Latin Maki and colleagues at Aalto University demonstrated the dynamic Casimir effect in a Josephson metamaterial, published in the Proceedings of the National Academy of Sciences. I want you to think about what this actually means. In 2011, in a laboratory in Sweden, physicists turned on a device and real light came out of empty space, not from a light bulb, not from a laser, not from any source of real photons. From the vacuum, the photons were entangled. They were real. They carried energy, and they emerged from nothing because the boundary of the vacuum was shaken hard enough to tear virtual particles apart and make them permanent. That is not marginal evidence for vacuum energy. That is the creation of matter from emptiness. Published in Nature, confirmed independently, and it was covered for approximately one news cycle before the world moved on to something else. I have spent an embarrassing amount of time trying to figure out why this did not become the biggest science story of the decade, and the only answer I can come up with is that people literally could not process the implication. Creating light from nothing sounds like a magic trick or a religious claim, not a laboratory result. But that is what happened. A team of physicists in Sweden, using equipment that could fit on a benchtop, created real photons from empty space. The photons were entangled, meaning their quantum states were correlated in a way that has no classical explanation. They were measured, they were characterized, they were real, and they came from nothing. If the Casimir effect was a nudge, the dynamic Casimir effect was a shove. It did not just show that the vacuum has energy. It showed that the vacuum can be made to surrender that energy in the form of real particles. The boundary between virtual and real, between potential and actual, between nothing and something, is not fixed. It can be moved. It can be breached. And the only thing you need to breach it is enough energy concentrated at a boundary that moves fast enough. There is an old philosophical question that usually comes up in late-night college dorm conversations. Why is there something rather than nothing? Quantum field theory has a very specific, very unsettling answer. There is something rather than nothing because nothing is unstable. The vacuum is not the absence of everything. It is the lowest energy state of everything. And that state is not empty. It fluctuates, it produces, it creates. If you perturb it hard enough, it gives you real matter. The distinction between something and nothing in quantum field theory is not a bright line. It is a threshold. But the dynamic Casimir effect, as dramatic as it is, was just one thread in a pattern that runs much deeper. Because the vacuum does not merely respond to moving boundaries. It responds to acceleration itself. And its response reveals something about the nature of reality that I find genuinely difficult to accept. In 1976, William Unruh at the University of British Columbia published a paper titled Notes on Black Hole Evaporation in Physical Review D, building on earlier foundational work by Stephen Fulling in 1973 and Paul Davies in 1975. The prediction they developed, now called the Fulling-Davies-Unruh effect, states that a uniformly accelerating observer moving through what an inertial observer sees as perfectly empty space, the Minkowski vacuum, the ground state, absolute nothingness, will perceive a thermal bath of particles. The empty space will feel warm. The Unruh temperature depends only on the acceleration. At Earth's surface gravity, 9.81 meters per second squared, the Unruh temperature is approximately 4 times 10 to the negative 20th Kelvin. That is so cold, it makes the cosmic microwave background look like a blast furnace. To reach even 1 Kelvin, you would need an acceleration of approximately 10 to the 20th meters per second squared. These numbers seem to place the effect permanently beyond experimental reach. But the experimentalists are closing in. In 2019, a team at the University of Chicago simulated Unruh radiation using Bose-Einstein condensates of cesium atoms and observed thermal distributions consistent with predictions. In 2202, Soda, Sudhir and Kempf at the University of Waterloo and MIT discovered that high-intensity lasers could amplify the effect to potentially measurable levels. And in July of 2005, researchers at Hiroshima University proposed using circular motion of metastable particles in superconducting Josephson junctions to achieve detectable Unruh temperatures of a few Kelvin. If any of these proposals succeed in the coming years, we will have direct confirmation that the vacuum looks different depending on how you move through it. And then there is Hawking radiation, the most famous prediction involving vacuum energy, which connects the quantum vacuum to the most extreme objects in the universe. Stephen Hawking's original paper, Black Hole Explosions, appeared in Nature on March 1, 1974. It was 2 pages long and contained an idea that stunned the physics community. Near the event horizon of a black hole, the extreme curvature of space-time amplifies vacuum fluctuations. Virtual particle-antiparticle pairs are created, and the tidal gravitational force separates them. One particle falls into the black hole with effectively negative energy. The other escapes as real radiation. The black hole loses mass in the process. It evaporates, slowly, over timescales that make the age of the universe look instantaneous for stellar mass black holes, but much faster for smaller ones. The Hawking temperature, for a black hole with the mass of the Sun is about 10 to the negative 6 Kelvin, far too low to detect astrophysically against the 2.7 Kelvin cosmic microwave background. But analog experiments have provided striking confirmation. Jeff Steinhauer at the Technion in Israel created a sonic analog of a black hole using Bose-Einstein condensates, where the role of light is played by sound waves and the event horizon is replaced by a point where the fluid flow exceeds the speed of sound. In 2016, he reported observation of quantum Hawking radiation in Nature Physics. In 2019, he measured its thermal spectrum in Nature. And in January 2001, he confirmed stationary spontaneous Hawking radiation through 97,000 repetitions across 124 days of continuous measurement, published in Nature Physics. The Unruh effect, Hawking radiation, the dynamic Casimir effect. Together they prove something that goes beyond any individual measurement of vacuum energy. They prove that the vacuum is not a fixed, passive background. It is an active, dynamic, observer-dependent medium whose properties change depending on your state of motion, your acceleration, the geometry of the space-time around you. The particle content of the vacuum is not intrinsic. It shifts depending on who is watching and how they are watching. And that, I think, is the deepest and most unsettling implication of this entire story, because it means the ground state of reality, the thing everything else is built on, the thing we call empty space, is not a fixed foundation. It is responsive, it changes, and we do not know what it is. I want to return to Max Planck for a moment, because his personal story casts a shadow over this entire narrative that I think deserves to be fully seen. After Marie's death in 1909, Planck remarried. His second wife, Marga von Hoslin, provided some stability, but the tragedies were far from over. His son Karl, born in 1888, enlisted in the German army and was killed in action at the Battle of Verdun in 1916. He was 28. Planck's daughter Greta, born in 1889, one of twins, died in childbirth in 1917. Her twin sister Emma then married Greta's widower. Emma also died in childbirth in 1919. In the space of 4 years, Planck lost a son and both daughters. He was 61 years old and had already given physics one of its most important ideas. The zero-point energy he had discovered 8 years earlier was by then established as a feature of quantum mechanics, embedded in the uncertainty principle, present in every equation that described the subatomic world. The mathematics kept working. The man who wrote it was breaking. The cruelest blow fell last. Erwin Planck, Max's youngest son from his first marriage, born March 12, 1893, had pursued a career in politics. He served as state secretary in the Reich Chancellery under the Weimar Republic. When the Nazis came to power, Erwin became connected to the resistance network that included members of the Abwehr and the old Prussian aristocracy. After the July 20th, 1944 assassination attempt against Hitler failed, Erwin was arrested by the Gestapo. He was tried by the Volksgerichtshof, the People's Court, under the infamous judge Roland Freisler. In October of 1944, Max Planck, 86 years old, the most distinguished living physicist in Germany, a man who had spoken directly to Hitler in 1933 to argue for the protection of Jewish scientists, tried desperately to have the sentence commuted. He wrote letters. He appealed to every remaining authority he could reach. He was reportedly told that a pardon was coming. It never came. Erwin was hanged at Plötzensee prison in Berlin on January 23, 1945. He was 51 years old. Planck called Erwin his best and closest friend. On February 18, 1944, Planck's home in Berlin-Grunewald had been completely destroyed by Allied bombing. His entire scientific library, all his personal correspondence, all his diaries, everything he had accumulated over 6 decades of scientific life was incinerated. He evacuated to Rogatz, a small town in Saxony-Anhalt. In 1945, he and Marga were rescued by American forces and brought to Göttingen. Planck wrote to a friend during this period, "You give me credit for too much if you think I have the strength to withstand this pain." But he kept working. He lectured into his late 80s. He told audiences that what remained to him was the possibility of following the advances his work had prepared and of responding to the wishes of people struggling for truth and knowledge. He died on October 4, 1947, in Göttingen. He was 89 years old. The Kaiser Wilhelm Society was renamed the Max Planck Society in 1948, a tribute that has endured to this day. The man who accidentally found the ghost in the equation, this residual half-quantum of energy that refused to vanish, lost everything that could be lost. His wives, his sons, his daughters, his home, his papers, his country. The 0-point energy survived all of it. It is still in the equations. It is still in the vacuum. It still refuses to go to zero. And more than a century after he stumbled upon it in a paper about radiation, we still cannot say what it is. I have been thinking about Planck a lot while working on this video, and I keep coming back to an observation that I cannot quite shake. The 0-point energy is, in a very real sense, the irreducible minimum. The energy that remains when everything else has been taken away. The thing that persists at absolute zero. The residue that survives even the most complete stripping down. And Planck himself was stripped down to nearly nothing. His family, his home, his records. Everything removed. And what remained was the work, the equations, the half-quantum of energy that someone would eventually have to explain. There is probably no meaningful connection between a physicist's personal suffering and the mathematical content of his discoveries, but the resonance is hard to ignore. The man who discovered that nature will not permit absolute zero, that something always remains, lived through losses that would have reduced most people to absolute zero. And he kept going, not because he had the strength. He said he did not, because the work demanded it. Let me tell you where we actually stand now, because the story is not static. The last few years have been more active than most people realize. Quantum energy teleportation, hot as once ignored protocol, has become a legitimate experimental field. Following the 2023 confirmations at Waterloo and Stony Brook, a Purdue team demonstrated both energy teleportation and energy storage using quantum computers in September 2024. These experiments prove that the entanglement structure of the quantum vacuum is not a mathematical abstraction. It is a physically accessible resource. You cannot extract free energy from the vacuum, but you can use quantum correlations already present in the vacuum state to move energy from one place to another in ways that were considered impossible 15 years ago. The DELIGHT experiment at Universitaris Saclay is attempting to observe vacuum optical nonlinearity, the deflection of light by light in empty space, predicted by QED, but never directly observed. If two intense laser beams pass through a vacuum and interact, even slightly, it would confirm that the quantum vacuum behaves as a nonlinear optical medium. Proof of concept results in air were published in Physical Review A in 2204, and the DESI Year 3 results, if confirmed by ongoing data collection, may transform our understanding of the vacuum entirely. If dark energy is not a cosmological constant, if the vacuum energy density evolves over cosmic time, then everything we thought we knew about the ground state of the universe needs revision. The static picture of a vacuum with a fixed energy density, off by 120 orders of magnitude, might be replaced by something far stranger, a dynamic vacuum whose properties change as the universe expands, a ground state that is not a state at all, but a process. And that brings me back to the question that has been open since the first minutes of this video. What is the quantum vacuum? What does it contain? And why has physics refused to answer? The honest answer, the one that makes physicists uncomfortable when you say it out loud, is that we do not know. And the reason we do not know is not that nobody has tried. It is that every attempt to answer the question leads somewhere catastrophic. Every path out of the maze ends at a cliff. If vacuum energy is real, if it is a genuine physical quantity that exists and gravitates the way general relativity says all energy must, then the cosmological constant problem is 120 orders of magnitude deep, and there is no credible mechanism to resolve it. Supersymmetry does not work. String theory's anthropic landscape is an explanation that explains everything and therefore nothing. No fine-tuning mechanism known to physics can naturally produce a cancellation to 120 decimal places. If vacuum energy is real, 10 to the 120th power worth of it is missing from the universe, and we have absolutely no idea where it went. If vacuum energy is not real, if it is merely a mathematical convenience, a bookkeeping device that produces correct predictions without corresponding to anything physical, then we have a different problem. The Casimir effect measured a real physical force between real physical plates, and the formula that predicts that force to 1% accuracy was derived by Casimir using vacuum energy as the physical mechanism. The Lamb shift, confirmed to 8 decimal places, was explained by Bethe, and later by Schwinger, Feynman, and Tominaga using virtual photon interactions with the electron, interactions sourced by vacuum fluctuations. Spontaneous emission rates change when you modify the vacuum. The dynamic Casimir effect produced real entangled photons from empty space. If vacuum energy is not real, then all of these experiments are measuring something, confirming something, producing something, and that something has no name. If the question is genuinely philosophical, if it truly lies beyond the scope of physics as Jaffe wrote, then quantum electrodynamics, the most successful quantitative theory ever produced by human intelligence, accurate to 12 decimal places, the theory that predicts the anomalous magnetic moment of the electron to a part in a trillion, contains at its mathematical core a quantity whose ontological status it cannot determine. The foundation of the theory is undefined, not approximately defined, not undefined. The formalism works, the predictions are confirmed, and the theory does not know and cannot determine whether one of its central quantities refers to anything in the physical world. I want to be very specific about what I am claiming here because I think this point gets lost in the abstraction. This is not a case where we know the answer and are arguing about the details. This is not like dark matter, where we know something is there and are debating what it is. This is a case where the most precisely confirmed theory in physics, the theory that underlies all of semiconductor technology and laser physics and atomic clocks and MRI machines and everything built on quantum electrodynamics, contains something that might not exist. And the field has decided that whether it exists is not a question worth answering. Peter Milone, in his 1994 monograph The Quantum Vacuum, demonstrated something remarkable and deeply uncomfortable. He showed that quantum electrodynamics can be consistently and completely reformulated entirely from the perspective of point fluctuations. Every phenomenon that the standard formalism attributes to virtual particle exchanges can equivalently be derived from the vacuum fluctuation picture. The Lamb shift, the Casimir effect, van der Waals forces, spontaneous emission. All of it. The vacuum fluctuation picture is not an approximation or an alternative interpretation of selected phenomena. It is a complete, self-consistent reformulation of the entire theory. And at the same time, as Schwinger showed, you can also derive everything without vacuum fluctuations. From a source theory perspective, where the vacuum contains exactly zero energy, both pictures are mathematically complete. Both give identical predictions, and physics has no mechanism, experimental or theoretical, to determine which one is correct. That is not a footnote, that is a crisis, because the two pictures have radically different implications for gravity, for cosmology, for the vacuum catastrophe, for the fate of the universe. If vacuum fluctuations are real, the energy is real, and general relativity demands that it gravitate. If they are not, then the cosmological constant problem dissolves. But we lose our physical understanding of why the Casimir plates move, why the Lamb shift exists, and why atoms spontaneously emit. The universe does not care about interpretive freedom. Either the vacuum contains energy, or it does not. Either that energy gravitates, or it does not. Either the 120 orders of magnitude discrepancy points to real missing energy, or it is an artifact of a formalism that we have been reading too literally. The answer has consequences for the large-scale fate of the cosmos. It is not a question that can be permanently delegated to philosophy, and yet it has been, for decades. Casimir was asked in 1972. He said he had not made up his mind. He was asked in 1983. Same answer. He died in 2000 without ever deciding. Fulling wrote in 22 that there is no proof vacuum fluctuations exist. Jaffe wrote in 05 that the reality question was beyond the scope of his paper. Wolfgang Pauli declared in his 1945 Nobel lecture that the zero-point energy has no physical reality. The formalism keeps working. The predictions keep being confirmed. The experiments keep measuring forces and shifts and photons that emerge from empty space. And the field that runs those experiments, the field that writes those papers, the field that has devoted more collective brain power to the quantum vacuum than to almost any other topic in physics, will not say what it is. I have tried, over the weeks I spent on this, to construct a charitable interpretation of this silence. The closest I can get is that physicists are waiting for a theory of quantum gravity to resolve the question. The cosmological constant problem sits at the intersection of quantum mechanics and general relativity, and perhaps only a theory that unifies both. String theory, loop quantum gravity, something not yet imagined, can tell us whether vacuum energy gravitates and how much of it there really is. That is a reasonable position. but it has been the position for 50 years, and the theory of quantum gravity has not arrived. Meanwhile, the data keeps piling up. The Casimir effect, the Lamb shift, the dynamic Casimir effect, quantum energy teleportation, the DESI results, the Unruh effect proposals. Each new experiment, each new measurement, each new theoretical insight adds to the weight of a question that the field has decided is too dangerous to ask in public. The ground state of the universe, the thing you are sitting in right now, the thing between the atoms in your body, between the molecules of the air, between the Earth and the Moon, between the galaxies. It is full of something. That something pushes metal plates together. It shifts the energy levels of atoms. It creates real photons from nothing when you shake it hard enough. It looks different depending on how you move through it. Its energy, according to our best theory, should be large enough to prevent the universe from existing. Its energy, according to our best measurements, is 120 orders of magnitude less than that. And the institution that discovered all of this, the institution that confirmed it again and again with increasing precision and decreasing uncertainty, has decided that what it means is someone else's problem. The real question is not whether zero-point energy exists. The experiments have answered that over and over with piconewton precision. The real question is what it means when the most successful theory in the history of physics has something at its center that it cannot name. Something it cannot decide is real. Something that produces correct predictions whether you include it or erase it from the formalism. Something that should destroy the universe but does not. Something that was found by accident in 1911 by a grieving man who was trying to undo his own greatest discovery. The vacuum is not empty. That is settled. What the vacuum is, what it contains, whether the energy in it is real or a shadow cast by the mathematics onto a universe that does not need it, those questions remain open. Not because they are unanswerable, but because the people who could answer them have decided, collectively and without ever quite saying so, that the answer is too dangerous to find. And the equations keep carrying it. The half quantum of energy that Planck found over a century ago. The ghost that Einstein killed and Heisenberg resurrected. The force that Casimir predicted and Lamoureux measured. The energy that should be infinite and is almost zero. The thing that refuses to go away no matter how many times physics tells it to. It is still there, still in the vacuum, still undefined, still waiting.